Okay, so let me see. Uh, yeah, so it's kind of what I said at the yesterday or during class. Just because I thought it was better to have some extra time today. I posted the quiz as some sort of assignment on Canvas, so you can upload it. I mean, I gave everyone until Saturday afternoon to post the solutions. So, so there's no quiz today. Well, yeah, in a sense, yes, because almost everything today, really almost everything in this course is row reduction echelon thing. So yeah, we'll continue doing that. There's almost nothing in linear algebra that won't use that. So yeah, we'll. I still have to tell you a couple more things, but yeah, almost everything will require reducing a matrix. There's almost nothing. There are very few things in the course that do not require reducing the matrix. So yeah, we'll continue doing that for sure. So what I was saying yesterday is that okay, what I was saying yesterday. So once you have a system of equations, you want to reduce it. Okay, you want to reduce it because that will make easier to identify what's going on in terms of the solutions. So for example, when we were reducing this system, right? If you start, well, you start with the system of equations. The first thing you always have to do is rewrite it in terms of a matrix notation. That's easy because that's just literally copy pasting the coefficients that you see here. Oops. So it's just really copying the numbers that you see here. That's the numbers here go into this matrix and the numbers here go into this vector. So I did like finding the matrix is kind of the easy part, and then you have to start reducing the matrix. Again, just using the three operations of switching rows, multiplying a row by a non-zero number, or combining rows. Okay, the idea is like again, you kind of get used to it, but and we'll do more examples today. But the idea is just to try to make as many ones and zeros possible, kind of like in a way like from you start with the first column, then you move to the second column, then you go to the third column, and so on. So it's always like organized in this way, just to give some structure to the method. Because if you start randomly somewhere else, like you're going all over the place. It gets to kind of do it in the same way every single time. And so once you get to the row reduced echelon form, if the system is inconsistent, that's very easy to identify because literally an inconsistent system will always have a bunch of zeros, a row full of zeros, followed by something that's non-zero here. So whenever you reach something like this, 0, 0, 0, 0, 0, 0, vertical line, non-zero number, that will be an inconsistent system. And that's how it will always look like. Because if you rewrite this in terms of the variables, this is kind of 0x, 0y, 0z, 0w. So there's never like all the variables go away. So you just get 0 equals 1. And then you're done because that cannot be solved, right? That's like impossible. So an inconsistent system is always easy to identify once you reduce the matrix. So that one is fine. The other one is, okay, then you move to the case of a unique solution. So, which is the example I was doing that I finished with yesterday. So in for example, in this case of a unique solution, you had three variables, right? There are three variables. By the way, yeah, I don't know if I think I said it yesterday, but I'll repeat it today. Like the number of variables in your system is equal to the number of columns of the matrix. But you start, so you have this system, you rewrite it in this notation. Okay, you start reducing using the row operations. Okay, and you get to something like this. This is what we got when you get to the row reduced echelon form. And if you just okay, I mean this is where we stopped when in the row reduced echelon form. If you check this, like that literally what's happening here is that once you rewrite it in terms of the original variables, x, y, and z, it just gives you it gives you an equation for a single, like, it's telling you X has to be this number, Y has to be this number, and Z has to be this number. So it's giving you a specific value for each variable. So that's why it's a unique solution. There's no choice in what the values of the variables could be. The fact that this was 0 equals 0, that's kind of saying that if you started with the four equations, kind of, if you think about the equations that's giving you some information, kind of there was some redundant information, because secretly one of the equations is contained, like the information of one of the equations is contained in the other three. Okay. So getting to 0 equals 0, it's fine. It's just saying that you kind of like had like some extra junk in the equations. So the way to identify that this is a unique solution is that if you look at the rank, so this is the easiest way to know for sure that there's a unique solution. If you look at the rank was just the number of non-zero rows of the matrix. So once you get to this form, to the reduced form, you count the non-zero rows. You have 2 and 3. So there were 3 non-zero rows, but that matches the number of columns, right? The number of columns is the number of variables in the system. So that means that if the rank equals the number of columns, there will be a unique solution. Basically, because there's kind of like an equation per variable. So if there's like an equation per variable, that kind of means that every variable should just have a specific value. Okay, so rank equals number of columns is a unique solution, and the case I haven't done yet is when rank equals is less than the number of columns. So in that case, there will be infinite solutions. So let's talk about the infinite solution case. So yeah, let's say I had given you something like this. Okay, this one should be fine. Let me just check it quickly here. Okay, so yeah, this one is fine. Okay, let's solve this system. Again, you have to rewrite it first in matrix notation. So let's do that first. You can write 1 minus 1, 1, 2, 1, 1, 5, 1, 3 times xyz equals 5, negative 1, 3. Okay, and then again, this is kind of like redundant. You don't care about it. So you can put like the vertical line just to do the operations. And okay, and we start again as before. So again, the idea is to you kind of start in column 1, and you you want to put as many ones and zeros as you can. So you already started with the 1. So that's good. So what you can do, once you have that 1, you can use this 1 to put a 0 here and a 0 here. Okay? So how can you put a 0? How can you put a 0 here? You have to do -2 row 1 plus row 2 into row 2. How can you put a 0 here? You have to do -5 row 1 plus row 3, and that is going to be replacing row 3. Okay, so let's see how this looks like. 1 minus 1, 1. Okay, so again, that just means multiply every coefficient of the first row by -2. Multiply every coefficient of the first row by -5. And then add that to the respective rows entries that you have here. Is that okay? Is that making sense? So that's how that looks like. I mean, again, in practice, this step is not, I'm not saying that you have to write it down explicitly. You can do it in your head. But I mean, maybe at the beginning it's always useful to see it written down. But I'm not expecting everyone to write this step because, like, just it's some space. And so you can just like write the result of these operations. Do this calculation mentally. That's usually how you do it, and you will get used to that over time. So you put here 3, you put a negative here, -11, and then 0, 6, and -2, and -12. Is that making sense? Is that okay? Let's just again here it's just super important to check everything to make sure that you didn't make a silly mistake with the arithmetic, because that can mess up your answers significantly. So far so good. Everyone with me? So once you get here, so that means that column 1 is oh, what happened? Oh, okay. That should be -25, right? Oops. Good. You mean here that it should be -25? Good, thanks. This is the sort of mistake that I'm talking about. This is what can be a problem. So thanks for that. Would have been a big thing. Yeah. So thanks about that. So double check every single calculation before going on. Otherwise, you you can do. Let's see. Okay. So you have to be careful. That's the thing. Imagine you were going to do that, right? So you want to use this -1 to put a 0 here, right? But if you do that, that would come at the expense of the 0 that you have here already, right? Because there's already a 0, and if you do 3 row 1, then you are going to make this a 3 again. Is that making sense? So, I mean, the idea is kind of not to mess up. It's not to mess up the ones and zeros that we have before. So it's not to use this -1 to put a 0 here. It's instead, what you should want to do is kind of put like a 1 here, and then use this 1 to put 0 up above and below it. Is that making sense? The last row will become 0. I'll explain that in a second, but I'm just saying that it's not. This is why there was this step where I said that the ones look like a staircase. I don't know if you remember that from last time. But the idea is to place the ones like in some sort of like descending staircase, because if you try to place the ones like at the same level, then it will mess up everything else. So one way to do this is like, if you wanted just to try to if you No, you can notice that this row is essentially twice the second row, but I'm not going to go that way. I'm just going to do it a little bit more slowly. I'm just going to put a one here first. So if you put a one here, how can you put that one there? Like you can divide row 2 by 3. And then is that making sense? And then I can use this one. Now I can use this one to put a 0 here and to put a 0 here. Okay. So let's try to do that. How can I put a 0 in the first one? I can do row 2 plus row 1 into row 1. And then how can I put a 0 in the other one? I can do -6 row 2 plus row 3 into row 3. So let's see, so I'm going to leave the same, the second row. So let me put it like this. And then I'm just going to add the second row to the first row. So I'm going to put, oops. I'm going to put 0, 1, -1/3, -11/3. And then I'm going to multiply the second row by -6. So you get, well, 0, and then a -6 here. And then when you do multiply this one by the last one by -6, you get 2, right? And then this one you get 22. Okay. And then I'll just add it to the other number. So I'm going to add this to the first row numbers. And I'm going to add that to the third row numbers. Okay, is that making sense? So, and now it's just do the arithmetic. So 0, then you get -1 is 2/3. And then -11/3 plus 5, that's 15, that's what, 4/3? 0, 1, -1/3, -11/3. So 0, 0, 0, 0. Okay. So far so good. Is that okay?
Professor, can I put so I see 1/3 times R2 right there. Can I also simplify the R3 at the same time I hear? So like
Right.
yeah. So
You could have done what, like say like R6, R3/6 or something like that, you mean?
yeah, something, or 1/6 times R3.
Right. You could have done those simultaneously. Yes, that would have been fine. Right. You could also have done R3/6 here.
Yeah.
Yes. And then you realize, oh, you end up getting the same, as the second row. I mean, at the end of the day, regardless of how you do it, you kind of realize that the idea is kind of to realize that if you look, every coefficient in the third row was like a multiple of the coefficients in the second row, and that's why eventually it had to go away, right? So that's the point. What I'm trying to say, that secretly what was happening is that kind of like the third equation was already contained in terms of the first two equations. That's why you're able to get rid of it and turn it into a bunch of zeros, because it's kind of not giving you anything new. So it looks like, I mean, in the system, yeah, we did start with 3 equations. It's just that some kind of like redundant information. So, well, it depends on what you mean by leave without fractions. Meaning, like you mean like rewriting this in a different way, or? Like you're saying, like just like leaving it, I would have like doing the like the addition. Like instead of divide by 3, could we leave? Well, I see. Okay, you could have like, for example, like you could have taken like row 2, right? Like you could have taken like row 2 and multiply it by 2, but at some point you do. I mean, if you want to put a 0 here, if you want to put like a 0 here, there's no way to avoid the fractions at some point. Like it's kind of necessary. Uh, yeah, like I mean, even if you want to leave this one without fractions, there will be a fraction here the moment that you make a 0 here. That's like unavoidable. So it's not like the fractions won't be that complicated in general. The denominators will typically all choose numbers where it's small, but yeah, I mean, sure, like you can avoid the fractions here by multiplying by 3. I think that's what they're saying. But I mean, like there's like a fraction here, and that the problem is that if you once we have to go back to the system of equations. So if you leave a 3 here, then this will be 3y. So in order to solve for y, you have to divide by 3 eventually. So you see, it's kind of unavoidable. You can escape the fractions at some point. You can delay it, but it cannot, if there's fractions, and there's not much you can do about it. Is that making sense? Okay. So column 1 is good to go. Column 2 is good to go. And then you get to column 3. The thing with column 3 is like, okay, maybe you wanted to make a 1 here, but you cannot make a 1 here without like messing up the stuff before. And that's why you actually stop already. I mean, again, at some point you will realize, you will kind of it will be kind of clear that this is where you have to stop. But if you still don't realize that, you just look at column 3. And yeah, you may want to make more ones somewhere, but like the only way to make a 1 here or a 1 here is by messing up the stuff that you had before. So you cannot create more ones without eliminating ones before or zeros. So that's why the process has to stop. But or again, you look at the definition for the row reduced form, like you kind of notice that it already is like is simplified as much as possible. But regardless of how you think about it, this is kind of the best you can do. And then once you rewrite this as a system of equations, again, once you have a system of equations, you just have to make the variable reappear. So you put it here, and this gives you what? Now it gives you x plus 2/3 z equals 4/3, and then y minus 1/3 c equals minus 11/3, and then 0 equals 0. Is that making sense? So just to compare, so you see what's happening here is that, again, of the 3 equations that we started with, of these 3 equations that we started with, secretly, some of the equations, one of the equations was redundant. So it's not giving you new information. So that's actually why there are only 2 genuine equations. So this problem, which appeared to have 3 equations, was actually like a problem with 2 equations. It's just that it was not so easy to tell that at the beginning because the equations were written in a more complicated way. But once you write it down in this more simple version, then you can see, oh yeah, there's only 2 actual equations in this problem. Okay, but you had 3 variables, right? So I mean, I don't know how much algebra you saw before, but if you have 3 variables and 2 equations, you cannot expect to give numerical values to the variables. the best that you can expect, like the best you can hope to do is to write like two variables in terms of one of the third one. So that's kind of what we're going to do here. So like the way to rewrite this system is just to say that x equals 4/3 minus 2/3 c, and that y equals minus 11/3 minus 1/3 c. Okay. And so what that means is that what is it saying? That whenever, so what's it, how should you interpret the system? This is saying that whenever you give c a specific value, then you have a value for x and y. So what's the interpretation here? So here's like the interpretation. Once you give z a specific value, you will get a value for x and you will get a value for y. X and y will acquire a fixed value, a specific value as well. But there are like infinitely, but there are like how many values can you give to the variable z? You can give infinitely many values to z. Z could be 1, z could be 0, z could be 1/2, it could be minus 2, it could be minus 1/3. You see what I mean? So, but c can take infinitely many values. So this system has infinitely many solutions. Is that making sense? So that's how again that's how the systems with infinite solutions look like. There, in the end, you will have fewer equations than variables once you rewrite it in terms of the row echelon form. So there's, again, like after you do a couple of these, there's no way to get confused. I mean, there's no way to get lost if you did the reduction correctly, because you will just end up with fewer equations than variables. So let me write that down. I mean, let me put it this way. So if you look at this, just to go back here, copy, paste. So one way to identify, so how can you identify the case with infinitely many solutions? If you look at the rank of this matrix, right? The rank of this matrix, remember the rank was just the number of non-zero rows. There's 1 and 2 non-zero rows, so the rank equals 2, but the number of columns of the matrix is 3, right? And so, and that's essentially what happens for a system of equations to have infinite many solutions. The rank is less than the number of columns. So let me write that down. So here's like a theorem or a fact. So for a system of equations, AX equals B, which is consistent, if the rank of A is less than the number of columns of A, let me put it in here with using some color. If rank of A is less than the number of columns of A, then the system has infinitely many solutions. because there are fewer non-redundant equations than number, because the number of non-redundant equations is less than the number of since the number of non-redundant equations is fewer than the number of variables. Okay. Is that making sense?
Professor, it's possible like when a larger than the numbers of the columns of the
Oh,
A.
that's a good question. That actually is okay, right? It's not, I guess. Wait, probably right. It's not so clear here yet, but that can never happen. Yeah, so you can never have the rank bigger than the number of columns. That's a great question, but yeah, I should make it as a remark. We'll explain later why that happens, why that's true. But yeah, that's a good point. So remark, you can never have rank of A greater than the number of columns of A. But of course, this is not clear right now. Yeah, this is not up. We'll see that why that's later on. We'll see that. Yeah, but it's a good thing to make a remark about. But we will explain that later. So it's really like yeah. So it's like, just to summarize, like inconsistencies, like an inconsistent system, like so. Okay, so just to summarize, is like what's going on here. You have a system AX equals B, and you have a row of zeros with followed by a vertical line that's a 1, right? That means that you have an inconsistent system, right? So that's how you identify inconsistent systems. You'll get zeros, vertical line, 1. Okay, that will always happen. So that's easy. And then if the rank equals the number of columns, is a unique solution. And if the rank is less than the number of columns, is what I just explained, it is infinite many solutions. Okay. Is that making sense? So that's kind of like those 3 things that kind of okay. So are there questions? How are we doing so far? So good. Let me see if I can show you this quickly. The graphics. Okay, so let me show you how these equations look like, because it's kind of nice to see them like visually. So just to show you, let's see if I can, okay, here it is. So let me enter on GeoGebra the 3 equations that we started with. So that's the first equation. Those are equations of what you call planes. And if you ever take multivariable calculus, you'll do more stuff with planes. that we're going to do here. Let me change the color. Okay, so that's the second plane. And you can see the right. Hopefully, everyone is being able to see the animation. And then you have the third equation, which is 5x plus y plus 3z equals 3. Okay. I don't know. Okay, so let's see. You have this. Okay, so you have these three planes. I don't know if it's so clear from the picture that the three planes kind of meet on a line. Can everyone kind of see that? So in fact, you can write the equation of the line. That's essentially what we just did. Because so let me put like the equation of a line here. Let's see if I can do it. I have to do it this way. So I'm going like if you remember the equation that I wrote at the end of the problem, I wrote x and y in terms of z. So you can put here 4/3 of x equals 4/3 minus 2/3 z, right? Then y equals minus 11/3 minus 1/3 z, right? Then z just z, and then you have, I mean, here, like, it's just like a bit tedious what I'm doing now, but I'm just saying, okay, yeah, here, I hope it, hopefully it looks better. I'm just saying x equals 4/3 minus 2/3 z, y equals minus 11/3 minus 1/3 z, and z equals z, right? That's kind of redundant, but you need to kind of write that on the algebra. And of course, I cannot plot this for infinitely many values in practice, so I just give some values for z. But let's see, did I write? No. Oh, okay, let's see. This doesn't look correct. Let me check. Did I enter anything wrong? It should yeah, it's like where's a mistake? Five seconds. Oh my God. I don't know if you can still see the PDF. I'll fix it on the PDF, but it had to be plus 1/3. Here, y had to be minus 11/3 plus 1/3 c. I'll fix it on the PDF. And now it's fine, right? Now it does look like it should look good. So that's the line of intersection. So you can see this, like, so what's happening here is that the three planes, you started with three planes, and they all the three of them happen to meet at a single line. So that's geometrically what's going on. So let me just fix, let me just fix on the note like the equations, because like I did make a small typo here. So yeah, the problem, the typo that I made here is that when I had this equation correct, but when I solved for y, this had to change signs. So this one should have been plus 1/3 of z. So just fix, I mean, if you're copying anything, just fix that, because that was a mistake earlier. I had written minus, it should have been plus. So far so good. Okay, now let me tell you two quick things. So there's a nice type of systems which always have a solution, which are called homogeneous systems. So homogeneous systems. They are systems of equations where the coefficients on every equation is where the coefficient on each equation is 0. The constant coefficient, the So what do I mean by that? Let me give you some examples. Here's a homogeneous system. X plus 3y equals 0. X minus 2y equals 5. This is a homogeneous system. Oh, sorry. Everything should be equal to 0. So this is a homogeneous system because you have 0 and 0 here. Here's another one. X plus y plus 2z equals 0 minus 2x plus 3y plus z equals 0. 3x plus 4y plus z equals 0. So this is also homogeneous because everything here is a 0. So in a homogeneous system, everything is 0 on the right hand side. Everything is 0 here on the right hand side. And you can put like, let's put another one like x plus y minus c plus w equals 0. And like, I don't know, 2x plus z plus w equals 0. So everything like this is 0, 0, 0, 0, 0, 0, 0. So it's always every single coefficient, every single constant here is 0. So my claim is that if you have a system like that, you can always at least solve it. There's always at least a solution to any system like that. Anyone can think about what could be what could all these systems have in common? What could solve all of these systems? What could solve this system? What values of x, y could solve the first system? What values of x, y, z could solve the second system? And what values of x, y, z, w could solve the third system? What could be what values for the variables might solve? Sometimes this solution is called the trivial solution because it's the most silly solution you could think about.
The xy equal to 0.
Just set everything equal to 0. So take x equals 0, y equals 0, z equals 0, w equals 0. Every single variable, just set it equal to 0. So what's every such system has at least one solution. Or let me write it this way. It's never inconsistent. Maybe it's better to put it this way. Inconsistent. Because you can always take each variable, because you can always set each variable equal to 0. You can always set each variable equal to 0. So for example, x equals 0, y equals 0, z equals 0, w equals 0, etc. Right? Like if you have more variables, you would have to set more equal to 0. But I mean, that makes sense because if you just plug in x equals 0, y equals 0, you get 0 equals 0, 0 equals 0. And again, here it will give 0 equals 0, 0 equals 0, 0 equals 0. So that's okay. So the nice thing about homogeneous systems is that they can always be solved. So the way in which usually like you write a homogeneous system is like it's written as ax equals 0, right? So and here means this is the vector whose entries are all 0, right? Vector whose entries are all 0. Are all 0. And so like the only thing that I'm saying is that if you're homogeneous, then the inconsistent case never happens, and so you only have two cases. So there are only two cases. So there's like a unique, remember, for a system, it's either inconsistent, one solution, or infinite many solutions. We already know this one cannot be inconsistent. So there could be one solution if the rank of A equals the number of columns of A, right? In this case, like that solution has to be the one that we just found. So it would be x equals 0. It would be the solution that you get by setting each variable equal to 0, which you can write kind of in this way. Or it has like infinite many solutions if or the other thing that can happen is that you can still have infinitely many solutions if the rank of A is less than the number of columns. So that's okay. But I'm just saying that at least for homogeneous systems, you don't have to worry about the inconsistent case that can never arise. So that's kind of good to know. I mean, it is, solving these are kind of easier because there's no need to keep track. When you solve an inconsistent system, a homogeneous system, you don't even need to keep track of the stuff along the vertical after the vertical line, because everything will be a bunch of zeros. So there's, you'll always get zeros there. But I mean, it's fine. I was just bringing this one up as a case, which is useful because it always has a solution. So that's kind of nice to know. And if you ever take differential equations, this is related to what's called a homogeneous differential equation. Like if you ever take 244. So I'll just make a remark here. If you take differential equations, these equations are related to the homogeneous differential equations. And those are really important in that if you ever take that class. Okay, so that's that's a special case of a system of solutions. And another important case is the following. Okay, and now I have to come back to discussing the matrix being invertible. So now I can tell you finally a better algorithm for finding the inverse of a matrix. So let's take a quick break of 5 minutes, and when we come back, I'll tell you, because it's more or less like kind of like the last thing that I wanted to include for the exam, I think. So I'll just tell you how to find in a more systematic way the inverse of a matrix. We already know how to do it, kind of, but I can now tell you a more optimal strategy. So let's take a quick break, and I'll tell you that once we come back. Okay, so let's get back to talking about inverses of matrices. So back to inverses. Oops. Here's like a high school question. Okay, let's start with the first high school question. I mean, it could be even pre-high school. I don't know. I don't know. How could you solve? How can you solve this equation for x? What would you write in terms of a and b? Yeah, and that gives you B over A, which I'll write now as A inverse times B. Is that making sense? So far, everyone okay with that? So the solution of AX equals B for numbers, right, is just X equals A over B, or sorry, B over A, or A inverse times B. So let's apply this to linear algebra. So now back to linear algebra. How could you solve? How would you solve AX equals B if you know A has an inverse? A has an inverse. Well, let's take this equation. I'm going to apply the same idea. I'm just going to write a little bit more steps. But so you start with this equation. The thing is, like, it's not kind of too appropriate to say divide by a matrix. Kind of like you have to be careful with that. It's better to say multiply by the inverse of the matrix instead of saying divide. Like the word divide is kind of a bad, dirty word in linear algebra. So don't say divide, just say multiply by the inverse. So what I'm going to do is multiply by the inverse of A, which is kind of equivalent to dividing by it, but it's just more appropriate to use the word divide, multiply. So it's just when you have an equation, you can multiply both sides of the equation by a number, or you could also multiply both sides of the equation by a matrix. Okay. So I'm just multiplying each side by A inverse. Okay. And why is that useful? What's the property of what does A inverse times A give you? That's what makes the inverse, right? It gives you, like, we know what A inverse times A is for a matrix. What is that equal to? What happens when the inverse of a matrix is that matrix? What would you get? You get the identity. That's the point of the inverse, right? Like the inverse is like the matrix that has that property that when you multiply with A, it doesn't matter the order for the inverse. A times A inverse or A inverse times A gives you the identity. Good. So this gives you the identity of size n by n, like if you're working with a square matrix. So you get I, like the identity times X equals A inverse V, right? But like remember, like multiplying the identity by a vector is like the identity is kind of like the number one. It's not really you doing anything. So you actually get that X equals A inverse V, right? Which is essentially the same thing that we would do in high school. You just have to be a little bit more careful here because again, the matrix multiplication is a little bit more subtle, but it is more or less the same idea. Okay, so what that means is that if a matrix has an inverse, like you can solve every system of equations involving A immediately. The solution is just A inverse times V. So let me write that down. So this is an important result. So here's an important result. So this is important. If A has an inverse, the solution to AX equals B is simply X equals A inverse B. In particular, notice that I'm actually giving you like a formula for what the solution has to be. So that actually means that the solution is unique because I have like a single answer. I just told you what X has to, the solution has to be. So that actually tells you as well that the solution is, there's only a single solution. But moreover, there's only one solution to the system of equations because it has to be x equals A inverse B. Moreover, this is the only solution. Then, in other words, when the matrix has an inverse, the system of equations is always consistent. It can always be solved and only has one solution. So, in other words, when A has an inverse, AX equals B can always be solved and always has a solution. Can always be solved and always has a unique solution. So that's why I'm about to do some examples before I tell you how to find the inverse of a matrix in general. But that's why it is important to know if a matrix has an inverse, because the moment you know a matrix has an inverse, that also tells you a lot of things about the systems of equations that you can build from that matrix. It just tells you that they always have a unique solution. So it kind of kills, of the three cases, it kills two of them. Just leaves you with the unique solution case. So just to give you an example about these, if you remember a couple of days ago, we had found some inverses. So let me give you some of the ones that we had found before. Okay, so just to give you an example. I think we had done this one in class before. So we had found, or it wasn't a quiz problem, I remember. So in class or a quiz problem, we found that the inverse of A equals 1, 2, 0, 3 was a matrix A inverse equals 1 minus 2/3, 0, 1/3. Okay, that's something we can compute. And again, in a couple of minutes, I'll tell you how to find this, like in general. But for now, like we had done this, so we had found the matrix had that inverse. So that means, like, so for example, if you wanted to solve let's say you wanted to solve this system, which is 1, 2, 0, 3 times xy equals 5, 2, right? So notice that this is ax equals b. So what I'm saying is that the solution has to be x equals a inverse b. That's essentially what I just said. So what is a inverse? A inverse is so that means that x is a inverse was 1 negative 2/3, 0, 1/3. So that was a inverse, and b is 5, 2. So this is a inverse b. So x has to be, and then you just do this multiplication. What do you get if you do the multiplication? So you get 5 minus minus 4/3, and you get 2/3. And this is 11/3, 2/3. So that means that x has to be 11/3 and y has to be 2/3 for this system of equations. So here, like, you didn't have to reduce the matrix, you didn't have to do anything, of course, provided you knew the inverse, right? So the question is, how do you, so everything boils down to finding the inverse, right? So the big question is really the inverse of the system of equations. And that's finally what I'm about to tell you. But maybe before I do that, is that okay? Are there any questions about this? So far, so good.
Professor, so how did you get inverse A? You use a equation A times A negative 1 power equal to infinity, identify.
Identity, yeah. I mean, that's kind of in practice how we did it before, if you remember. But now we're going to now we're going to do it. I mean, it's kind of we're going to do it the same way, but in a slightly. I mean, it will look slightly different, and the way I'm going to write it, it actually is more convenient. But yeah, it's kind of we're going to do that again, but now with in a way that kind of looks more convenient to solve. But yeah, that's kind of how we were finding it before. So, and what I'm going to do now is kind of do that again, but in a more efficient way. So let me explain how to find A inverse in general. So I'll illustrate this in the 2x2 case, and then I'll just give you the general formula. So let's just start first for like a 2x2 matrix. So imagine that your matrix is like A, B, C, D, right? And you want to find A inverse for A. So again, I don't know what A inverse is going to be. I just know that I need times A inverse to be the identity, right? That's a defining property of the inverse, right? So I don't know what A inverse is. Since I don't know what it is, you have to just give some new names to the entries of that matrix. So call A inverse X, Y, C, W. And you'll see why I'm writing it this way. But the thing is, like, I just don't know what that is. So I have to find like a formula for it, right? And so you have to do AV CD times XYCW equals 1001. Is that okay, everyone with me? So that's kind of like what we were doing before. It's just that before I would give you specific numbers for this for the matrix A. So in general, you know, you would never see this part. Like we only were giving like variable names to A inverse, right? But now since I want to do this for the general 2x2 matrix, I have to call its entry something. So I'm just going to call it A, B, C, D. Okay, and 2x2 matrix times a 2x2 matrix. That's a new 2x2 matrix. What are the entries of this two new 2x2 matrix? So it's AX plus BY, then dx plus dy, and then a z plus bw, and zz plus zw. Is that making sense? So again, remember that an equation for matrices is an equation between matrices is an equation between the corresponding entries. So let me equate these. I'm going to equate them. You'll see in an interesting way. So let me put these two first in pink. Hopefully you'll notice something fun that's happening here. You'll see why I'm choosing the to break it into to write the equations in this particular way. Okay. So I just wrote the equation like that. I mean, there are 4 entries, so you get 4 equations. But can anyone see why? Is there maybe clear to anyone like why I kind of, you know, wrote these 2 first and then these 2 second? What's happening here? I don't know if you can see like something fun that happened. Is it I don't know, how should I say it? Like what's happening here is that the first 2 equations, right? What are the variables that appear in the first 2 equations? Only x and y. And what are the variables that appear in the in the 2 last, in the third and fourth equations? Only c and w. So it's kind of like a weird system of equations because kind of like the 4 variables don't appear in all of them simultaneously. It's only they come in pairs. You know what? Is that making sense? So the variables appear in pairs. So what that means is actually that I mean it's sure it's 4 equations, but since variables appear 2 and 2, you actually can solve 2 separate systems of equations. Is that okay? Because they kind of don't interact with one another if the variables are not mixed, right? Is that making sense?
Yes.
So it's kind of like a fun thing that happens when you're trying to find the inverse. That like yeah, you had 4 variables, but they kind of come in 2 and 2. And then if you notice, something more fun even occurs because if you rewrite this as a matrix, right? What do you get here? You get A, B, C, D, right? Times X, Y equals 1, 0. And you get here A, B, C, D times ZW equals 0, 1. Let me write that. I need a little bit more space. And A, B. Right? And that's fun. That's what's curious about this. It's more clear if you kind of write it in the vertical line notation. If you write it in the vertical line notation, what are we getting? What's happening? Can anyone see what's going on? What's happened is literally you're solving 2 systems of equations and the same matrix A is appearing on each of them, right? So you have here the matrix A and you have here the matrix A. The only thing that's changing is the vector that I'm putting here. Okay? Right? But is that making sense so far so good? So what that means is that actually, since it is the same matrix on the left-hand side for these 2 equations, like what you can do is kind of like combine these 2 into a single, put one after the other because like the operations that you're going to use to reduce this matrix are the same operations that you're going to use to reduce this matrix. So it's kind of like to save yourself, to cut your time in half, you can just put like what we can do is kind of like combine this into a single mega system where I just put A, B, C, D, and then here put 1, 0, and then 0, 1. Right? So just copy paste this ones here, and that's what we're going to do. What's happening here is that you have the matrix A, and here you have the identity matrix. And so what that means is that to find the inverse of a matrix, you just have to solve a system of equations where the matrix A is like set equal to the columns of the identity matrix. Okay, so let me write that down. If this derivation didn't make a lot of sense, like don't worry about it. I'm just going to write the algorithm. But let me put it here. So here's like the algorithm, and this is the algorithm that we're going to use for finding A inverse in general. So here's the idea. To find the inverse of a matrix, you make the system, you consider the system A identity. Okay, and you try if you can reduce A. Okay, if you can reduce the matrix A to the identity matrix, then the matrix that you get up to the right of the vertical will be the matrix you get. It will be once I do the examples, this will make more sense. But the matrix you get to the right of the vertical line will be A inverse. So what I'm saying is that if you start with A augmented with the identity, and you can get to the identity on the left-hand side, then whatever this becomes will be A inverse. And if A can't become can't be made equal to the identity, can be made the identity, then A doesn't have an inverse. Okay, so I'm going to do some examples right now, but it is a lot easier than what may sound from it as I'm writing it. You'll see it's very, very simple to do. It's just like a kind of like a system of equations you have to work on, but it is not too bad. So let me do like let me start with some examples first. So let's start with the matrix that I just wrote. So let's do that. This matrix A to 1, 2, 0, 3. So here's some examples. A was 1, 2, 0, 3. So how could I find A inverse? So how to find A inverse from this method? Okay, you consider A with the identity. So what is A is 1, 2, 0, 3. And what's the identity is 0, 1, 1, 0. Okay, so it's just kind of, you copy paste the matrix and then vertical line followed by the identity. It's always the same. And then you have to try to reduce this as much as possible. Okay, it's because secretly this is two systems of equations. Is this matrix with this vector and this matrix with this vector. It's just kind of we're doing two at the same time to save ourselves some time. But how do you try to get the row reduced here? Well, this column is already good to go. That's nice. But what about this column? Well, I want here now, right? So I need a row 2 over 3. So let's put that down. So I'm just dividing row 2 by 3, so you get 0, 1, 0, 1/3. Okay, because again, I just think that you're doing two systems of equations simultaneously. This one, this thing, this one, and then this one with this column. It's just that since it's the same matrix, I'm kind of repeating this. There's no point in doing the steps twice. So it's kind of like a way to save yourself time. And then how do you put a 0 here? Like you do minus row 2 plus row 3 plus row 1, right? So if you do minus 2 row 2, sorry. If you do minus 2 row 2 plus row 1 into row 1, let me just put like the end result. You get 0, 1, 0, 1/3, right? And then what happens if you put a minus 2 row 2 plus row 1? Well, this one doesn't affect the 1 here, so you still get a 1. I mean, I'm choosing this one so that it would kill these 2, so you get a 0 here. And then this one is not affected because there's a 0 here, so when you multiply by minus 2, you are not affecting that. And then you put minus, then you're multiplying this by minus 2, so you get minus 2/3. Okay, and so since you reach here to the identity, that means that whatever you get on this side has to be the inverse. So the inverse in this case has to be, so A inverse has to be 1, 0, minus 2/3, 1/3. Is that making sense? Let's do, I'm about to do some more, but just want to check if this is making sense so far. Exactly. The goal is, I'm about to do one that fails, but the goal is try to get the left-hand side to the identity. If you succeeded, whatever junk you have on the right-hand side is the inverse. If you failed, the matrix has no inverse. So it's very straightforward. So let's do one. Let's do one that's even 3 by 3, so that you see that this is not just like exclusive to 2 by 2 matrices. So let's do one for 3 by 3. So let me see. Let me find an example here. Let's see. Let's see. Okay, I will do. Yeah, I'll do some more here. Oh yeah, let's do I mean, this is a fast one, but let's say I had given you, here's another example. Let's say I give you this matrix, which is looks nice. Okay, so I give you this matrix, right? And I am asking you now, does this matrix have an inverse, right? Yeah. So my question is now is does A inverse exist? Okay, so what do? You put the matrix A, which is 1, 0, 1, 0, 1, 0, minus 2, 1, minus 2, and you just put vertical line identity. So you always do that. So you put 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and then you try to see whether you can make this side you try to get this side to the identity, and we just have to check whether we succeed or not doing that. So how do you try to make this the identity? Again, you start with column 1, you have to put a 2 here. Sorry, you have to put a 0 here. So to put a 0 there, let me do 2 row 1 plus row 3 into row 3. So that's going to affect only row 3. So I'm just going to use a different color for row 3. Okay, so when you do these operations, again, like these operations, usually you can do them in your head. So it's 2 with -2 gives you 0. This one is also already 0, so 2 times 0 is 0. So with 1, that gives you 2. And then 2 with -2, so it gives you 0. And then what you get in this side, you get 2 with 0, you get 2. And then 0 with 0, you get 0. And then 0 with 1, you get. Okay, so that's what that would give you, right? And then let's do a next step. And I cleaned column 1, have to go to column 2. I already have a good 1, that's good. Now have to make a 0 here. How can I make a 0 here? I can do -2 row 2 plus row 3 and substitute that into row 3. And what happens here when you do that? Well, again, 0 with 0 is 0. Now this is -2 with 2, that's 0. 0 with 0 is 0. And then 0 with 2 is 2. Minus -2 with 0 is -2, right? And 0 with 1 is 1. So this one is what that gives, right? And what happened here? You get a row of zeros in the end, correct? Let me use a different color.
Professor, why on the using R2 R1 plus R3 got R3 on the blue line?
Mhm.
The second column's 2. How did you get it? Because I got a 1 here.
Okay, so are we talking about this step? Oops. Are we here, or should I go to this
Sure,
one?
go up. Yeah, this one. Because I
Okay,
got a
so
different number.
So you're saying why? Okay, let me check. So I'm doing 2 row 1 plus row 3, right? So which is you're asking me about one of these.
The last row.
Oh,
The last row.
okay. Last row. Why did I get? Oh, okay. I see what you're saying. Why did I get like a 2 here?
I
Right.
get a
That's what you're
2, yeah.
asking.
It's a complete.
Why did I get a 2? There should have been no reason to get in a 2. Good. Is that everything else is fine?
Let me check.
Yes, this is where it's very important to stop me before I do something else that's silly. Is that yeah? I was like kind of I look accidentally at the one here. So yeah, it's okay, yeah, it's 2 row 1. Yeah, because it's 2 row 1 plus row 3. So yeah, everything else looks fine, correct? I'm going from here to here, so everything else looks okay. Yeah. But thanks for pointing that out. So what that means is that now the operation, instead of having multiplied by -2, you only have to multiply by -1. So it will still give you a bunch of zeros, but this does change a little bit. It would change to -1. Okay, so yeah, this is like that's what I'm saying. Like you're doing this operation so many times that just increases the chances of a silly mistake somewhere. So it still would have worked for what I wanted, but yeah, it would have been like an incorrect reduction. It still worked just in the sense that I still get like a row of zeros, right? which is what I wanted to get to. So since you get to a row of zeros, there's no way to turn this into the identity matrix, right? Is that making sense? So this can never be turned into the identity. So that means that this A inverse does not exist here. Is that making sense? So again, if you get to the identity, then you're good. There will be an inverse, and the inverse is whatever you have on the right side. If you don't get to the identity, actually, that means that the matrix did not have an inverse to begin with. Let me see. Let's try to do another one. Let's do one more to make sure that this is making sense. Correct. It's not. I mean, it's kind of right. It's not giving you the solution. It is giving you the solution for a specific system. I mean, like for example, here where there was an inverse, right? It is giving you the solution to. Sorry, let me show you what I mean. So where is okay? So for example, here, this is actually this is giving you a specific solution, like but to only you know where like the right hand side is 1 0. Sorry, I should have started here. Where the right hand side is 1 0 or the right hand side is 0 1. So it's just giving you it is secretly two systems of two systems of equations, right? So it's just that but we kind of don't think about it that way. We just think about it, oh, we're trying to find the inverse. Once you have the inverse, then you can just solve every solution, every system of equations involving A using this formula, right? So, but I mean, yeah, secretly there is two systems of equations hidden in here, which were like these two that, these two that I wrote before, but it's kind of very specific values for the system of equations. So, but it's just like a means to an end of finding the A inverse. Once you have A inverse, then you do just do the multiplication of A inverse with whatever numbers you truly care about to find the solution. Is that making sense? So it is like a solution, but it's not like it's a very specific solution. So it's better not to think about it that way. Just like think about it as a method to find A inverse, and once you have A inverse, you use this formula to find the solutions. But in this particular case, yeah, in the case that it didn't have an inverse, there will be no solutions, correct? To these equations because like this would have been inconsistent or things like that. So, I mean, for these particular numbers. But yeah, it's better just to think about this as something separate, as a way to find the A inverse. And if you have the A inverse, then you can just use a formula to find the solution to the system. Let me do another one. Another 3x3, so that just to get used to the 3x3 case. Okay. Okay, let's find the inverse. Here's another example. Just to make this one faster, determine if A inverse exists for A. Determine three, 2, -1, 1. 3, 0, 0. Okay. So I give you this 3 by 3 matrix, and I want to know whether there's an A inverse for this matrix. What should you do? Same thing. That's what you call augmenting it to the identity matrix. So just put this matrix together with the identity. 1, 2, 3, 2, negative 1, 1, 3, 0, 0. Then 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and let's try to, I mean, as you can see, like in practice, like usually this can take a little bit of time. So typically these matrices have a couple of zeros in their entries to begin with, so that it's a little bit faster to find the inverse, like for practical purposes. It's kind of just to get more like the idea of what's going on. So I'm going to do -2 row 1 plus row 2 into row 2, right? That will give me a 0 here. And I'm going to do -3 row 1 plus row 3 into row 3. And that will give me a 0 here. So let's see what that gives me now. So I'm going to use row 1 as a standard. 1, 2, 3, 1, 0, 0. So when you do, okay, again, if you find a mistake that I'm doing, just let me know immediately, because otherwise it can screw everything up. But this goes with this, so you get a 0. Then this one becomes -4, right? And then -4 with -1 is -5. Then this becomes -6, and then this becomes -5 again. That's good. And then this one becomes -2, and then this one is 0, and then this one is 0. Okay, and let's see the other one. There should be a 0 here. That's how we chose it. Then -6, -6 there, and then -9 or -9, right? Then -3, and then 0, 1. Okay, so I think this is fine, right? Hopefully I didn't make any silly mistakes. And then I'll put, okay, column 1 is ready. Go to column 2, put a 1 here, right? So you can do -1/5 of row 2. And there's nothing that has been affected. Okay, and then yeah, with this one I can put zeros and zeros here. So let's just do it. -2 row 2 plus row 3. Sorry, plus row 1 into row 1. And then 6 row 2 plus row 3 into row 3. Right, that's a way to get a 0 here and a 0 here. Okay. So it's -2 row 2. So this gives you 0. And then this one is -2. -2 with 3 is 1. Then -2. So you get here. Okay, it's better to write this one out because it's fractions, so I don't want to get confused. 1 minus 4/5, right? And then this one is 2/5. That one is 0. And then just look at the last row is 0, 0. That's good. And then, okay, this is -3. Okay, let's see. And then we're getting there, right? So 6 times 2/5 is 12. So it's just -3 plus 12/5. And then the other one is -6/5. And then each one. Okay. So it's better to simplify the fractions a little bit before going on. So let's see. So it's 1/5, 2/5, 0, 2/5 minus 1/5, 0, and then -15, 3/5 minus 6/5, 1. Okay, we're almost there. And hopefully by now you can see that we're going to reach the identity. We just need a couple more steps. So this will have an inverse, but still we don't have the formula for the inverse. So to get the inverse, you just have to put like -1/3 of row 3, because we need a 1 here. That one is easy, so let me put it first. So -1/3. So, almost there. -1/3 is -1/5. Ooh, this is 2/5. And this is okay. This is not that bad. And then finally, to get to the identity, we just need 2 more row operations. I mean, this is going to be the identity. So I need less space for this one. So when you do minus row 3, you get 1/5. I mean, you get 2/5 on this one. You get 0 on this one. You get 1/3 on this one. And then you get 3/5 here. You get -3/5 in this one. And then you get 1/3 in this one. If I did it correctly. So if the calculations are correct, an inverse should be 2/5, 0, 1/3. 3/5 minus 3/5, 1/3. 1/5, 2/5 minus 1/3. Ooh, is that making sense?
Professor, question. So we already get the one. So could you go up a little bit? For here, we already got the inverse A, but why we keep going to simplify?
Well, no, you still don't have the inverse because this is still not the identity, right?
Oh, yeah.
It's just that once you get, I mean, even once you're here, right? once you're here, it's clear that you're going to win, to succeed, because you're just going to make a 1 here and then get rid of these 2. But it's only until it literally looks like as the identity here that you can claim that the right-hand side is the inverse. So in any previous step, the only thing that can happen is that it may become obvious that there will be an inverse, but until you finish the procedure, you don't know for sure what the inverse is. Is that making sense?
Yes.
So yeah, just now, okay, just to wrap this up quickly. Okay, so the one thing you can always do, okay, so hopefully now you get why, like these computations, like reducing the metrics is not too bad in the sense of what you need to do. It's just you're having to do so many operations in your head, involving multiplications and subtractions and additions and then all these things, that it is easy to mess up in some entries. So just be, I mean, I have done it like 2 or 3 times already today, right? So just be careful when you do these things, because like, it's very common to just make a mistake when you're doing so many operations. Yeah, there's like, well, again, that's one of the nice things about linear algebra, that really so many things have like an algorithm for. So you can go to Wolfram Alpha and that's like to check the inverse of a matrix. Let's see. Let's see. 1, 2, 3. Oh, did I copy it? It's 1, 2, 3, 2, -1, 1, 3, 0, 0. And is this going to be the correct? Oh my God, is this the correct inverse? Did I copy something wrong here? 1, 2, 3, 2, -1, 1, 3, 0, 0. Okay, so it looks like I did make a mistake. I don't know where this happened. Like it's what happened here? Let's see. Is this? Yeah. Okay. Yeah. No, it does seem like I'm. Okay, so let me just check it quickly to see what could have gone wrong, because it doesn't appear to match. It's kind of similar. I mean, there's some rows that are kind of similar to what we have, but it's not quite what we have. Okay, so what I'll do, this is kind of the last topic that I was going to include for the exam. So there will be a couple of things that will, if you check the study guide, there are things referring to the transpose of a matrix and things like that. I'll remove them from the study guide because I just didn't get time to cover it. So I'll send you like a revised version of what to study for the exam. Just we'll delete a couple of topics. So if you want, you can leave right now. I'm just going to fix this on the iPad, the notes, because it does seem like the inverse formula here has like a mistake. So I prefer to just have like a clean version. Yeah, it has to be like a subtraction somewhere. So I'll just fix it. I'll record it on the video in case you want to watch this, or if you want to stay, you can stay. We'll just try to do this quickly. But it's kind of like, yeah, it's kind of annoying because like you try to, you may have, let me see if I can find it out quickly where this happened. It's on Monday. There's an announcement that has that information. You should check for an announcement called information about the exam. What I was saying is that I will send an updated version about it, just to, okay, this one seems fine. Okay, I think this one looks fine. Then this one, yes, this one also seems fine. -3, here 1. Correct, it's on next Monday, yes. And then let me check here. 1, 2, 3, 1, 0, 0. And then when you do 0, 0, 1. Okay, this one also seems fine. Okay, now we're good. Now let me see what happened here. So what happens when you do -2, 2? Yes, to 5th. Okay, this looks fine also. Uh-huh. This looks fine. Okay, this looks also okay. And then I simplify here. And then 5, 1/5, 2/5, 0, 2/5 minus 1/5, 0. Okay. Ah. Okay, this is fun. This is minus 15. So minus 15 becomes minus 3. Here it is. Whew. Oh my God. The minus 3/5. Okay. It wasn't so close to the, I mean, it was kind of close to the end, so that's good. But it was a sign because I wrote 3/5 when I should have written minus 3/5. Okay. And now we're back on the game. So once you do that, this becomes a 1/5. Everything else seems to be fine. Let's see if that fixes everything. So now when you do the operation, again, this one was 1/5. So that's the only one that affected it. So, yeah, it does make a difference here. Like this changes a little bit, like it becomes, because now this one becomes a 0, and then this one becomes 1/5. Uh-huh. Let's see if that's correct now. Is this correct? Let me, and this one will be 1/5. Let me check again on Wolfram Alpha. 0, 0, 1/3. 1/5 minus 3/5, 1/3, 1/5. Oh, okay. Yeah. This wasn't too bad. I'm glad. Okay. Let's go. Let me show you. Now this does match the. Now the entries do match the entries on Wolfram Alpha, but it just shows you how much like you just make a very stupid mistake of a sign somewhere, and then all the entries start affecting, start changing. So it's kind of useful to keep that in mind. I mean, it's very important before you move to the next step, you just redo every single calculation, like check all the arithmetic. Yeah, now this is fine. So yes, what I was saying is that I'll send you sometime later today, like a revised version of the announcement for the exam, because yeah, like this, there was like some stuff about the transpose of a matrix, which I guess we can discuss it later. It's not too important right now. So, and a couple of other things I'll simplify. So yeah, so I'll send the announcement in a couple of hours. But it's basically so the exam will be basically what we're doing: finding the inverse of a matrix, solving systems of equations, finding like the matrix that takes a vector to another vector. I mean, that's kind of like the only couple of like we have only been doing like 3 or 4 things so far. So that's what the problems on the exam going to be like. I had sent like some practice exams, but I also changed them a little bit to make them slightly to just adjust it to a more easier version, because yes, since we don't have the transpose yet, then like there are a couple of things that I cannot really ask right now. So I'll send like a simplified version of everything later today. And yeah, now I did finish, so you're free to leave if you want. So but yeah, the information is on the announcement, but I'll fix that announcement then.
Professor, so we have a question. If I have a simple way, I don't have to like step by step to figure out a question, right? Like the website is showing us, his way is used like 1/over 15 times the whole matrix and got a number.
Okay. So the thing is like there's like this formula called the Kramer rule. Kramer's rule for finding the inverse of a matrix. But the question is like the thing. Okay, so there is a formula for the inverse of a matrix, which involves something that's called the determinant of the matrix, right? We still haven't talked about the determinant, but actually in the 3x3 case, kind of like because then you have to ask how do you obtain these coefficients, right?
Yeah,
Because these
sometimes kind of
it is right.
useful way have to so complicated, there's so many steps, and maybe sometimes
Right.
just mess up and
I-
then the mistakes.
in the thing is actually to find this formula, you have to, there's kind of no free lunch, like if you have heard that phrase. There's this other way to, I can show you actually what Kramer's rule says. That's like what Wolfram is writing here. I don't know if it's on the, yeah, but it's going to give you the, okay, Kramer's rule for inverse. Kramer's rule for the inverse. Or if not, I can show it on Wikipedia. Let's see. Yeah. So here's the thing. Yeah. There's this other way to find the inverse of a matrix using Kramer's rule, but if you read what it is, I can promise you that it is not that much better than what we're doing, because it also involves tons of multiplications, because like there's this thing called the determinant, which we still haven't talked about, but then you would have to find the determinant of the matrix, which we still haven't talked about. But let's put that aside. Let's say you want to learn that on how to do that. That's fine. And besides finding the determinant, then you have to find a bunch of other determinants. And so you end up doing like 20, 30 multiple. I mean, it is not, and this formula is harder to memorize. Like it's just not, I can assure you that it is not that much better. What you can do, at least in the 2x2 case, I guess it's fine. I don't mind it. That one is easy to memorize. So if anyone wants to memorize it, then they're free to do so. Where is the information for the exam? Here it is. So this is the one that I said I was going to simplify a little bit, but did I write it here? Okay. Okay, I think, where did I put it? I have it somewhere. Okay, I will add it to the notes for the study guide. Inverse of a 2x2 matrix. Okay. Yeah, but where is the formula? Okay. The inverse of a 2x2 matrix is, there is a relatively simple formula for the inverse of a 2x2 matrix, which is this one. This one is relatively okay to memorize. So yes, if you want to memorize this one for the 2x2 case, then you can do that. For the 3x3 case, like the one that you get from this Kramer's rule, there's like an analog of this formula for the 3x3 case, but that I don't find that much better it is not so simple to memorize. I mean, you know, for the exam problem, I'll just probably give you like a matrix to begin with that has a bunch of zeros or whatever, so that it's easy to get to the identity. But yeah, for the 2x2 case, if you want to memorize this formula, then yes, you're free to do so. But for the 3x3 case, I just think you will end up, keeping that in mind will just like be more confusing, I feel.
So in the exams only like 2 times 2 or 3 times 2?
I mean, I would never ask like the inverse of a matrix of something bigger than 3x3. That would take forever.
Okay. Sure.
And if it's 3x3, probably again it would take less time to simplify than the one that we just did. The thing with the one that we just did is that I think this one had almost it had very few zeros. Like it would be a bit easier to simplify. So yeah. But yeah, like this, the point is that finding the inverse takes time. All these things take time if the systems of equations are too big. So yeah, practically speaking, I cannot give you anything too big, you know.
Okay.
So right, yeah. So I wouldn't it's not. But yeah, I'll send a revised version of the practice exam and all these things later today, just so that it doesn't include those topics that I was planning on including originally. So yeah, but yeah, I wouldn't worry too much. I mean, I wouldn't put anything that would take an eternity to solve. You know what I mean? So it won't be the problem. The matrices won't have massive coefficients, or like, they won't be anything too long to do.
Gotcha.
It's more like a conceptual thing. Like, do you know what you're supposed to do? Yes or no. If you're good, if you know, then you get it in a couple of minutes, and it won't take you that long. Were you going to ask me something else?
Okay. Yeah, about the exam, like, do you have more projects questions?
Well, that's what I was saying. Like if you check on the announcement on Firefox,
Yeah, I saw it. They have a two
yeah,
exam
right.
one, two.
I have to fix those. I mean, I will just change them a little bit to adjust them more to what you actually covered. But besides that, like again, the thing is like besides that and the practice on the PDF, there's not, that's more or less already. There are not that many variations of problems we have been doing. The only thing that varies is like the coefficients of the equations, but there are not many different things we have done so far.
Okay.
Really, like the only thing we have done so far is kind of like reducing a matrix. If you think about it, that's kind of 70% of what we have been doing. It's just that, of course, if you start varying the coefficients, there's the systems of equations can look different, but they're not too diverse the problems we have been doing. So, yeah, between the practice exams and the problems of the PDF that I recommended, which I'll change the recommendation because again, like some don't no longer exist. And if you go through the examples we have been doing in class, and yeah, that should be more than enough.
Okay.
Because it's not like, yeah, you'll see there's not really that many different things we have been doing once you go over the notes. So
Okay. I understand. Thank you so much.
yeah, sure. Yeah, sure. Good.
Have a nice day. Bye.
You too. Bye. You too. Anyone else? Okay.